Hello, everyone. Welcome to the fifth week lecture. Today we will be looking at functions in general. Last week we concluded sequences and series, and those are functions in a very specific manner. And today we will look at a broader picture of what functions mean in mathematics. In today's slides, we will be looking at the basic definition and properties of a function in order to know when we are dealing with a function and when we're dealing with something else, which is mapping things. We will talk a little bit about different number sets and domains. And I guess in the end, we will get a feeling for why functions are just a very fundamental element of mathematical discourse. Right off the bat, let's start with repeating a bit of the stuff we had about 3 weeks ago when we were introduced to sets and mappings. So, what exactly is a function? I gave you here on the slide the formal definition. So, we just call the object of a function with some variable. Here it's called f. And a function in itself describes how two different sets are related. So we have two sets with a bunch of elements, x and y, and it describes the relation from x to y. Very important, this is a unary relation, so it goes from x to y, not the other way around. And the formal correct way of denoting the function is the one expressed here. You define it by saying, okay, here we have f. It's defined as the function going from x to y. So the first thing you have to specify are the domain and the codomain. And then the second thing you specify is the actual algebraic expression of the function. So f of x would mean the algebraic expression, which tells you how to compute f of x from x. If this was an actual function, then f of x would be equal to, I don't know, usually something with an e and x squared and so on. But this is the formal way to express functions. Now, of course, oftentimes we encounter just, okay, f of x equals e to the power of x, and we still know what's going on. How can it be when the formal way of expressing a function is this? Well, this usually comes from a place where it's implicitly clear what the domain and the codomain are. Usually when you are working on any mathematical problem, which is dealing with functions, but the problem is not specifically from mathematics, but just an application problem, we just assume an x and y are real numbers because this is the most powerful and at the same time easiest to handle set of numbers. So we just assume x and y are both equal to the real numbers. But of course, this does not have to be the case. And if we want to properly specify our function, we have to say what kind of sets we are talking about. Now, in order to recap, let's start by looking at a function with finite domains. So assume x and y are finite. The important property here for this to be a function, for this set of arrows to be a function, is once that all the arrows face from x to y, and secondly that there is one and exactly one arrow leaving every single element of x. Because that's the very core idea of a function. We take a domain and we assign every single element of this domain a value. So every single element of x has to be assigned a value and exactly one value. That's the important thing here. And then if we look at y, there's many options. Like every single element in y can either be reached once or twice or never, basically an arbitrary number of times. So in general, a function can have any mathematical set as a domain. from the empty set, which of course is kind of useless in most cases, up to highly elaborate sets, like the complex numbers, or even beyond that with quaternions and so on. Every well-defined set can be a domain. Most importantly, though, domain and codomain can differ. They do not have to be the same. As I said, in most application cases, they will just both be real numbers, but they can be different. We can map, for example, integers to real numbers. For example, if we want to express which athlete had which time in a race, for example, then we assign every integer a achieved time in a race. So in that case, for example, the domain and the codomain would differ. In itself, this does not really matter much, but afterwards there will be some properties of functions which will be of interest to us, and there we can utilize this idea that if domain and codomain differ, some further things change. But more on this later. Another thing to watch out for is that domains do not have to be one-dimensional. A domain can also be a vector space, because a vector space in mathematics is nothing else than another set. We will, of course, not dive deep into this because it's not super relevant, but it's probably useful to keep this in the back of your head, that the term of a function is much more general than all of the real number applications that we will be looking at. A little heads up, in the slides, all those capital N's, R's, and Q's that look kind of quirky, those are the terms for the sets. So the N here on the slide is the integers, the R is real numbers, and the Q is the rational numbers. I know this is not the proper mathematical expression, and I will try to fix this in the future slides. Okay, so a good example for a function is a sequence. A sequence is a specific type of function, as I already mentioned. And with a sequence, the domain is already given. So the domain of a sequence is n, the integers, as we assign every integer a value, but the value can be any real number. So if we have n as our domain and r as our codomain, we are talking about a sequence. And maybe one thing which you will wonder, well, what makes sequences specific as functions? If you look at a sequence, at its plot, I don't know, if you're a programmer, you might call it a scatter plot, right? Just dots all over the place. Whereas with what we usually would call a function is something with a graph, like something with a line that you can draw with the pen, which goes through your figure. And what I'm currently talking about is the notion of continuity, and this will be covered in the next chapter. But it's important to keep in mind that the distinction between integers and rational numbers will become very important. Okay, in the rest of the lecture, we will mostly be talking about the specific properties of different functions. But before diving into this, I want to discuss a little different topic, which is the expression of functions. So as you remember with sequences, there was an explicit and a recursive form of expressing them. And the explicit was very powerful, whereas the recursive was difficult at times. Series were always defined in a recursive way, and oftentimes we were interested in finding out things about them for which the explicit form would have been useful. And with functions, we usually have the explicit form. That means we are given two domains, and then there's an algebraic formula which gives us the rules of obtaining the image of an element x in a domain. For example, f of x is x squared or something. This is the normal case. However, keep in mind that does not necessarily need to be the case. For something to be a function, an algebraic expression to compute the image is not necessary. Take the following sentence, for example. The function mapping the calendar days to the number of new COVID-19 infections in a country. This function maps the days in a year to their respective number of new COVID infections on that day. And this is no function that we can obtain in any sort of practical way analytically, right? There is no underlying 1 divided by x squared times e to the whatever, right? It's just natural circumstances which make up the function which describes this. And the true underlying distribution function is unknown, right? There's no way to obtain it. There's no way to give a formula of it, at least in a precise, non-erroneous way. However, it is still a function because every day gets assigned its number of new COVID infections. It's just a contextually defined function. These are not functions we will analyze deeply because if you don't have an explicit form of the function, there is no real way to discuss it mathematically. Sometimes there is, but this is between difficult and impossible. So these types of functions exist, but we will not be dealing with them. The second important thing, which you will, on the other hand, encounter quite often, are piecewise functions. So let's consider you have the domain of the real numbers, for example. It may very well be that, for example, the algebraic expression describing how your numbers behave in the negative domain is different than the positive domain. Take the simplest example here, the absolute value of x. So the absolute value of x can just be expressed as the absolute value of x, but we can also express it as a piecewise function. For example, if we have a negative domain element, so x is smaller than 1, we map it f of x onto negative x. And on the other hand, if our domain element x is positive, we map it onto the identity, onto f of x. And in a sense, you can just cut your domain into an arbitrary set of intervals and just define a function for every partial interval as you like. This is perfectly fine, makes it a bit more complicated to express a function, but it has the same properties as a function which just has one explicit form, one explicit expression which describes all elements of the domain. Afterwards, when we talk about continuity, it will be important to see if the boundary values are the same. So let's say we have an interval which goes from, I don't know, negative infinity to 0, and then one that goes from 0 to infinity. Then it becomes interesting to see how the two piecewise defined functions interact at the point 0. So do they match or are they offset? And if they match, do they align, or is there suddenly a corner in our function? This will be discussed further when we talk about continuity. Okay, so now let's get to the real important stuff. The question I'm about to ask is very much a core question about within the study of calculus, within studying and understanding functions. So assume we have a function and we're mapping each element of the set x to elements of the set y. Now we hit a few elements of the set y. The question is, can we go back from y to x? Can we find a function that maps from y to x and, well, ends up in the same place that we came from? And if so, why? And if not, what's the limiting factor? Now, importantly, y maps to x has to fulfill the definition of a function. This means every element of y must have a mapping onto exactly one element in x, right? So naturally we can ask the question, the function f x maps onto y. What can be wrong with it? Where can it go wrong such that this becomes impossible? So here again we have our image from a few slides ago, mapping from d set x to d set y. Imagine we land through the arrows in the set of y, and now we want to map back to x. What kind of problems do we encounter? Maybe pause the video for a second and think about it. What prevents us in the endeavor of going back from y to x after arriving at y? Okay, I hope you gave it a thought. Now here's the reason. We've landed in the set of y and we want to go back. There's 4 elements a, b, c, d, and by the definition of a function, every single one of them has to get a value in x. However, there's no arrow pointing towards a. This means there's no value that will be assigned to a, and thus this is per definition no function, since a does not get a value. This is the first problem. And the second problem is at the element of b, because if you think back to the definition of a function, in a function, every domain element has to get exactly what value it gets mapped to. However, there's 2 arrows showing to b. This means that there's no unique or deterministic way to say which value b is mapped onto. Thus, b gets 2 values, and this is forbidden for a function. So this poses a second problem, which means that there is no function for going back from y to x. So you've heard the 2 terms, which I'm going to redefine now again already before, but I thought it was quite important to recap them as they will be a focal point about our analysis of functions. So for the first one, it was the first property we just looked at the finite set. So the formal definition is the following. Assume you have 2 elements in your domain, a and b, and their functional values are the same. Now, if for any a and b, where this is true, it follows that a has to be equal to b, then f is called injective. This is the formal definition, and it is defined in such a backhanded way in order to be able to prove it easier afterwards. So the intuition behind what we're talking here, injectivity, is that every element in the codomain is hit once at most. We look at the codomain, and no element is allowed to be hit more than once. This is the intuition, but we need this formal expression in order to afterwards be able to prove or disprove it, in order to be able to plug in a function and see if it actually holds. And this is called injectivity. The second one is if you imagine an element, let's call it A, of the codomain, if there always is an element of the domain X such that f of our element, f of b, is equal to a, then we have surjectivity. The function is called surjective. This means that every single element of the codomain is actually reached. For example, if we're mapping from the real numbers to the real numbers, every single real number is hit in the image of our function. And if our function is injective as well as surjective, so every element of the codomain is hit at least once and at most once, or exactly once, then our function is called bijective. Now, I know we had this before, but once more, why is this so important? The point is that with bijectivity, another very important property comes into play, and it's a property I was talking about beforehand when I was asking, is it possible to go back from y to x? And for this, we state the following theorem. The two statements which you can read here are equivalent. A function is bijective if and only if a function is invertible. And invertible just says exactly what your intuition here means. It means that when we map from a domain to a codomain, we can reverse the operation and go back from the codomain to the domain. The formal definition of an inverse function to which a function is invertible is the following. You call the inverse function f to the power of -1, and it has the property that if you concatenate them, so this means you take the function mapping a domain to a codomain, and then you use the resulting codomain as a domain for your second function, expressed as right here on the slide, you get back to x. This means that the two things basically annul. You have your ordered set of the domain, you take your function, then you take the inverse function on top of that, and then you should be back right at where you started. Then you're having an inverse function at your hands. For this, I would like to go over a simple example. Consider the following function. We are mapping real numbers to real numbers, and our functional term f of x is equal to x. So we're mapping every element to itself. Now, let's just analyze if our function is injective, and let's analyze if it is surjective. Now, think back. What was the definition of injectivity? It means that every single element of the codomain is hit at most once. So let's just disprove this with contradiction. Let's just assume that there's two elements a and b, and their functional values f of a and f of b are the same, and that then a is not equal to b. This would be a counterexample to injectivity. However, we know that f of a is a, because this is a functional term, right? F of x equals x, so f of a equals a. And we know that a is not equal to b, which again is equal to f of b. So we just proved that f of a is not equal to f of b. This contradicts our assumption. This means that our assumption that a is not equal to b must be false. This again means f must be injective. All right, then to the second property. We have to show that every element of the codomain is hit once at most. So again, let's assume the opposite to prove this by contradiction. Let's assume that there is some a in the codomain such that there is no b in our domain in a manner that f of b would equal to a. How can we find a contradiction? Well, f of b is equal to b, right? Just by the definition of a term, f of x is equal to x. But b may now not anymore be included in the domain, because if b was part of the domain, then, well, f of b would be equal to a, right? But this contradicts our assumption that we have identical domains. We just figured out that if A of the codomain is never hit from the domain, this would mean that this particular element can't be in the actual domain because everything maps onto itself. But we have identical domains, so we have a contradiction to our assumptions. And if we have a contradiction, this means that our assumption is wrong, and since we assumed a negation of our theorem, the theorem itself is true, and f is surjective. And since it's both surjective and injective, it's bijective. This means there is an inverse function. So let's compute the inverse function. It is defined as the function such that f to the power of -1 of f of x is equal to x. And we can just plug in the value of f of x. The value of f of x is just x. So we get f to the power of -1 of x is equal to x. So this means that the function and the inverse function are the same. And this is a special type of function. Here we're mapping every element onto itself. And this function is called the identity. The identity is always bijective, it's always invertible, and it's in a sense the trivial function. This, of course, holds true for all other possible sets. In every possible set, the identity has this property of being bijective and invertible. Now, a second example where this doesn't work out is f of x equals x squared. Now, again, assume we have a and b such that f of a and f of b are equal. Let's just say that b is equal to -a. Well, f of a is equal to a squared by the definition of our function. And a squared, on the other hand, is also equal to f of -a. This means that if b is equal to -a, both a and b have the same functional value, although a and b are different. Thus, there's two different elements in our domain that are mapped onto the same element of the codomain, and our function is not injective. And similar for the surjectivity condition, assume the element -1, -1 out of the real numbers to be the element of our codomain. Now we can ask, well, every single element of our codomain has to have a pre-image, but what is the pre-image of -1, right? So what squared is equal to -1? And the simple answer is nothing. There is no real number which squared yields -1. Thus the function is not surjective, as not every element of the codomain is hit. As you can see, disproving injectivity and surjectivity can be significantly easier than proving it, since one counterexample is sufficient. All right, I hope you made it so far. Again, I have a few sample exercises for you, which I will present to you now quickly. And I recommend you to pause the video, take a little break, and see if you can solve them. And in the end of the lecture, we will go over to solutions of the sample exercises. Okay, so I've written down 3 functions, and your task is to determine their injectivity, surjectivity, and bijectivity properties. And additionally, you're supposed to say if it is bijective, what is its inverse function. Pause the video and take your time. Okay, so another thing I would like to quickly discuss is cardinality. This is roughly talking about the size of sets. In order for a function to be bijective, and this, in my opinion, makes a lot of sense, both domain and codomain have to have the same number of elements. Because if you remember, bijectivity meant that every element of the codomain is hit exactly once. And if there's more elements in the domain, then necessarily some codomain elements have to be hit more than once. And if the codomain is larger, then some elements will be left over. And this is a very simple argument for small domains. If our domain has 4 elements, but our codomain has 5, there is no way to hit the fifth element. Necessarily, at least one element of y will not be mapped to, and surjectivity will not be held up. However, this becomes increasingly more complicated when talking about the infinite domains. Take a simple example. Assume we map every single integer to, well, the corresponding odd number, even number, I'm sorry. So assume we're mapping n to 2n. We're doubling every integer in order to get a even number. You would be right to say that intuitively there's twice as many integers than there's even numbers, right? Because when we just take the even numbers, we take out every second number. However, in set theory, this is not necessarily the case, because both sets are countably infinite. I will talk more about this in an upcoming voluntary lecture on cardinality and countability. But for now, the intuition you should go with is that if something is infinite, but you can assign an index to every single number, it is countably infinite. The mathematical notion is that, of course, there's twice as many integers than there's even numbers, but for every single integer there is, no matter how large it is, you can just take it by 2 and get a even number, and for every even number, you can divide it by 2 and get another integer. So there is a strict and well-defined relation that maps an integer to an even number, and thus the entire function is bijective. You can go one way and you can go the other way. And so countably infinite in this sense is the cardinality that we're dealing here with. And when we deal with rational or real numbers, things change. Rational real numbers are not countably infinite. I will dive a bit deeper into the upcoming voluntary lecture, but for now, keep in mind that cardinality can be an easy way to argue that bijectivity is impossible. Okay, thanks for staying until the end of the lecture. I just quickly wanted to give you the solutions on the exercises you hopefully did. So for the first exercise, neither of the conditions is given. There are multiple domain values mapping onto the same codomain value, and inversely there's many values in the codomain which are never hit. In the second example, we are only surjective since we're going from negative infinity to positive infinity. And in the third example, we actually have a bijective function. We said that this function was neither in the previous examples in the slides. However, we did a tiny change to the domains. We said that we are only looking at the positive real numbers, and for the positive real numbers, square root of x is a valid inverse function of x squared. Thanks for listening, everybody, and hope to see you joining in on the next lecture.